Welcome to lesson 5-6. So today we're looking at definite integrals and substitution. So in previous lessons, you've already learned how to evaluate a definite integral using the fundamental theorem of calculus. So of course that involves finding an antiderivative and then evaluating it at the upper limit minus evaluating at the lower limit. And you also, just a couple times ago, learned about how to find an antiderivative using substitution. So what this lesson is doing is combining those two ideas together. Now, evaluating a definite integral that involves substitution, it's going to start the exact same way, but there's going to be an important difference, and that has to do with those limits of integration and having to worry about those. So let's go ahead and take a look at an example here. I'm going to show you how to do this particular example two different ways. First, I'm going to just show you sort of what you would probably guess is the method, but then I'm going to show you the way that you really are intended to think about that pays a little bit more attention to the limits. Okay, so to start with, again, if I'm going to evaluate this, I need to find my antiderivative, and of course that means I'm going to need a substitution here. Hopefully x squared plus 1 is jumping out at you as your u. So we're going to let u equal x squared plus 1. So du is 2x dx, or in other words, dx is du over 2x. Okay, so now when we do that substitution, I'm going to leave off those limits for just a moment. I'll come back to them in just a second. So we've got the 2x times, and then now we're going to have u to the fourth, and then our dx, remember, is going to turn into du over 2x. So of course that 2x and that 2x are going to cancel out. But here's the problem. Remember that this du is indicating that this entire integral is in terms of u now. And if I'm going to have limits of integration, that this du is indicating that those limits are values of u. But the problem is these are actually values of x. So one thing we can do to indicate that is to actually now write this as x equals 0 and x equals 2. So yes, we are combining different variables, but at least we're staying consistent with that. So when I clean this up, what I really have then is the integral from x equals 0 to x equals 2 of u to the fourth du. And now we can just go ahead and evaluate this definite integral. So now we're going to find our antiderivative of u to the fourth, and that's going to be u to the fifth over 5. And we're evaluating that from x equals 0 to x equals 2. And of course now we're going to substitute back in for u. And that's going to give us the quantity x squared plus 1 to the fifth over 5. Again, evaluated from 0 to 2. Now I don't have to put x equals 0 and x equals 2 anymore because now our function is back in terms of x. And then now we can just evaluate this. So this is going to be 2 squared plus 1 all to the fifth over 5 minus 0 squared plus 1 all to the fifth over 5. All right, so 2 squared is 4, 4 plus 1 is 5, and then 5 to the fifth is going to give us 31/25. And then 0 squared is 0 plus 1 is 1. 1 to the fifth is still 1. And then I ran out of room here, so I'm just going to put it up here. So finally we get 31/24 over 5. Okay, so that's probably what you would expect in terms of evaluating a definite integral when we had to use substitution. But like I said, you are intended to actually understand how to do this where our limits of integration also change. So now let's do this problem a second time, showing you what you're intended to do with those limits instead of keeping it as an x equals. Okay, so we're still starting the same way, so we're still going to identify that our u is x squared plus 1, our du is 2x dx, and that makes our dx du over 2x. So again, that means over here we're going to still have the 2x, this is now u to the fourth, and this is du over 2x. But like I said, the other thing that we're going to do then is we're going to change our limits so that our limits are also values of u. Now, but remember, that means we have to somehow translate from an x value to a u value. But that's exactly what that first definition of u does. It tells us how to find u in terms of x. So if my lower limit is 0 when x is 0, then that means u is going to be 0 squared plus 1, which is 1. And then when my upper limit x is 2, then that means u will equal 2 squared plus 1, and that's 5. So this is now the definite integral from 1 to 5 when it's in terms of u. So when I clean this up, I have the definite integral from 1 to 5 of u to the 4th du. And again, now I don't have to put u equals, because remember the du is already telling me that these are values of u. So now, to evaluate this, same thing, we're going to find our antiderivative. That's going to be u to the 5th over 5 from 1 to 5. But here's the nice thing also. Because 1 and 5 are already values of u, and this is also a u, we don't have to substitute back in for u. We're actually substituting the 5 and the 1 right in there. So this immediately just becomes 5 to the 5th over 5 minus 1 to the 5th over 5. And this is exactly what we still ended up with in the previous problem when we had substituted x, values of x, into x squared plus 1. We basically did the same calculations, we just did them in a different place. So again, this is going to end up giving us 13/24 over 5. And I totally just flipped those numbers. That should be a 31/24 over 5. Thank you to those of you who are sitting at home saying, no, that's not right. Okay, so now, the reason that it's important for you to be aware of this particular approach, because you might be thinking, well, can I just use the first way? And the answer is yes. If you're just trying to evaluate a definite integral and it involves substitution, you can use either of these two methods. It doesn't really matter. However, the AP exam has in the past assessed this particular method on the multiple choice, and this is how they did it. They gave a problem similar to this original integral and said, if you were to evaluate this using substitution, which of the following definite integrals would you end up with? And so one of the choices might be the integral from 0 to 2 of u to the 4th du, but another choice might be the integral from 1 to 5 of u to the 4th du. And if I hadn't shown you this particular method, and you didn't think too closely about the limits of integration, it's very likely you would have chosen A, when in fact that's not correct. Again, because those limits are values of x, but this integrand is supposed to be in terms of u. So the correct answer here would have been choice B. So this is how they have assessed this particular technique on the AP exam in the past, and I wouldn't put it past them to be able to do something like this again. So it is important for you to be aware of this issue about changing your limits of integration. Okay, so really that's the lesson. So there's not really anything particularly new for you to know. It's just that we do have to pay close attention to those limits of integration. So let's go ahead and take a look at one more example here, though, just to show you something else that could happen in the course of changing those limits of integration. So right here we've got the integral from -6 to 1 of x over the cubed root of 2 minus x dx. So of course we are going to rewrite this as the integral from -6 to 1 of x times the quantity 2 minus x to the -1/3 dx. And so now hopefully we recognize that u is going to equal 2 minus x. So du will equal negative dx, or in other words, dx just equals negative du. So when we substitute, we're going to have an x times u to the -1/3 times, and then dx is going to be a negative du. That x didn't cancel out, so that means I do need to substitute again. So I'm going to solve this equation for x. So if u equals 2 minus x, and that means x is going to equal 2 minus u. And then also, remember, we need to change those limits of integration. So when x equals my lower limit negative 6, u is actually going to be 2 minus negative 6, which is 8. And for my upper limit, when x is 1, u is going to equal 2 minus 1, which is 1. Now notice, the lower limit, negative 6, turned into a bigger number. But we don't automatically put bigger numbers on the top. You have to keep the limits where they were in relation to the original values. So when I rewrite this, that negative 6 in my lower limit, that now turns into an 8. That positive 1 stays as a positive 1. Okay, so now, again, we're also going to replace that x. So I've got 8 to 1. My x is going to get replaced with 2 minus u, and then this is going to be u to the negative 1/3. And I've got that negative. I'm going to put the negative out in front. And now our integrand is fully in terms of u. All right, so now let's go ahead and distribute that u to the negative 1/3 before we do anything else. So I have the negative integral from 8 to 1 of 2u to the negative 1/3 minus u to the 2/3. All right, so now we're going to have the opposite of, so this is going to be 2u to the 2/3 divided by 2/3 from, and then minus u to the 5/3 divided by 5/3, and that's going from 8 to 1. Let's go ahead and simplify that a little bit. So when I flip and multiply, that's going to become 3u to the 2/3 minus 3/5 u to the 5/3 from 8 to 1. And so now we can evaluate that. So I'm going to put the negative all the way out in front. And so now we're going to have 3 times 1 to the 2/3 minus 3/5 times 1 to the 5/3 minus 3 times 8 to the 2/3 minus 3/5 times 8 to the 5/3. All right, so now we have the opposite of, so this is just going to, of course, going to be a 1 and a 1. So I have 3 minus 3/5 minus, now 8 to the 2/3, remember the cubed root of 8 is 2, and then 2 to the second power is 4. So I have 3 times 4, which is 12, minus, I have 3/5 times, now the cubed root of 8 again is 2, 2 to the 5th is 32. And let me go ahead and move up here since I'm out of space. So again, I have the opposite on the outside. Don't forget about that negative, because otherwise you're going to make a sign error. So here, let's see, we've got 3 minus a 3/5 minus a 12, and then remember, don't forget to distribute the negative sign, so plus, so 3 times 32 is going to be 96/5. Now, since I'm doing this by hand, notice 2 of these fractions already have a common denominator, and then 2 of them are just normal integers, so I'm just going to combine the ones that I can first, rather than trying to get a whole bunch of unnecessary common denominators. So 3 minus 12 is going to give me negative 9, and then negative 3/5 plus 96/5 gives me a positive 93/5. And then now I need to get that 9 over a 5, but at least it's just one number that I have to change. So this is now a negative 45 over 5 plus 93 over 5. So negative 45 plus 93, that's going to be 48. So positive 48 over 5, but then remember we have the negative in front, so we get negative 48/5. All right, and that's basically the lesson. So again, the main idea here is if you are evaluating a definite integral and you have to use substitution in order to find your antiderivative, you do need to make sure that you consider that you have to change your limits of integration as well. All right, good luck.